We're starting. Ladies and gentlemen, welcome to FSR events. Every Wednesday, we have an FSR event. This week, it is FSR Talks. Research and expertise coming from outside the Florence School. So we are presenting what the others do, and we are discussing with them. It is co-chaired by Ilaria, Conti, and me. But Ilaria knows the topic 10 times better than I do. So Ilaria will immediately jump to drive the discussion. Ilaria, the floor and the session are yours.
Many thanks, Jean-Michel. Thanks for the introduction. Indeed, well, it's very difficult actually to find real experts on today's topic because indeed with this today's online event, what we really want to do is to open a new box, to test, to discuss with our real experts today that I will introduce in a minute, a new technology, a technology to produce hydrogen, which could be, as the title of today's online event suggests, unproven or underestimated. So we are going to try and answer this question, whether this new wave, almost unknown process to produce hydrogen is a technology which is still largely unknown because it is unproven, because it is at a fairly stage of development, or whether it could be indeed a great technology with a lot of potential to decarbonize the energy system, and it's just for the moment underestimated. But step by step, first of all, I'm trying to give a little bit of context to why we decided to open this box today. As you know, the European Commission published last year its hydrogen strategy, which is quite ambitious, as we all know, and you know that this is a topic that we've been following quite closely in Florence School since already a couple of years. Ambitious plans to develop mainly renewable hydrogen. Plans include 6 gigawatts by 2024 and 40 gigawatts of renewable hydrogen by 2030. So having now the target, most of the debates are focusing on how to reach these targets. And we know that there are plans included in the hydrogen strategy to develop electrolyzers, being considered at the moment the main way to produce renewable hydrogen, or green hydrogen as we want to call it. But there could be alternative ways, and that's exactly photocatalysis is exactly one of those, together with others that we discuss in other contexts, of course, pyrolysis and so on and so forth. So we are going to address this topic with our two speakers today. Trevor Best, he's the CEO of a company called Syzygy Plasmonics, and precisely involved in the development of photocatalysis. And we are having as a discussant today Ronnie Belmans, professor at KU Leuven, and also co-founder of EnergyVille and our main FSR expert on decarbonization from a more technological side. So I'm really happy to have both of you here. I will give the floor first to Trevor for an introduction. He will explain us more about photocatalysis, and then Ronnie will comment on Trevor's presentation, and then we will open, as usual, the floor for questions. So please do not hesitate to write in the chat box, and we will try to deliver your questions to our speakers in the second half of the event today. Trevor, you're welcome, and you have the floor.
Hey, thank you so much, Ilaria. It is wonderful to be presenting to all of you today. I hope that this is a fun and informative session for everyone involved, and looking forward to answering any questions that you have. So before I get started with my presentation, I would like to give a quick introduction on myself. My name is Trevor Best. I am the CEO of Syzygy Plasmonics. I spent about 10 years working in the energy industry in the United States. I worked for a large industrial player called Baker Hughes. They are primarily involved in oil and gas extraction, and my co-founder, Dr. Suman Kadiwada, and I worked in their R&D division. It's called the Center for Technology Innovation in Houston, Texas. We worked there, each of us worked there for about 5 years or so, and together we were involved in more than 100 R&D and product development projects. So we got very, very comfortable with new product development. We were very committed to finding low emission alternatives for the oil and gas industry. And in our experiences, we struck out on our own and started looking for technologies that could cause a massive positive impact in the world's fight on climate change. And ultimately, we came across this, what we're going to be talking about today, which is the antenna reactor photocatalyst. And after an extensive due diligence where we tried to break the technology, we found that it was quite exceptional and decided to start the company. And we opened our doors, so got first money in and opened our doors in February of 2018. And since then, we've scaled the technology about 500,000x. And we've improved the efficiency more than 100x. But we will get into all that and some of the history of photocatalysis and all that fun stuff today. So let me share my screen. Fantastic. So to really understand what it is that Dr. Suman Kadiwada and I found, we need to take a step back, zoom out a little bit, and look at human society. And what we see is that thermal catalysis, this is using heat to perform chemical reactions. Generally, that heat comes from burning some kind of fossil fuel. You know, thermal catalysis is really a foundation of modern society. And, you know, from thermal catalysis, we make fertilizer, which feeds everyone on the planet. We make fuel, which is how everyone and all products get around the world. We make plastics, and we make chemicals and other raw materials that make all of the products we use. And of course, we make hydrogen, which everyone is very excited about right now. These products, they're responsible for trillions of dollars in revenue. And things like fuel and fertilizer, they support about 1/3 of the global GDP. Unfortunately, burning fuel to power these processes is responsible for about 3.5% of all carbon emissions. And indirectly, things like fuel, when you combust it to get around, it's responsible for about 1/4 of all carbon emissions. So the problem that Syzygy is trying to solve with our photocatalyst is that industry needs to dramatically reduce these emissions without distressing the global economy. And so how we do that? So Syzygy is taking our photocatalyst and we are using it to electrify chemical manufacturing. So we replace heat that comes from combustion with light from LEDs and renewable electricity. So by electrifying chemical processes, we allow them to run on renewable electricity, and we help to eliminate their carbon footprint, which supports our vision of driving a gigatons of CO2 emissions reductions by 2040. So, you know, this all sounds great, but why photocatalysis? This isn't the only way that we can electrify chemical manufacturing. I'll give you some good examples by comparing it against the status quo. So status quo today, you have some kind of fossil fuel input. You know, you are combusting that to produce heat. Unfortunately, this is also producing carbon emissions. This means that the environment in the reactor is very high pressure, high temperature. That means you have to build the reactor out of very, very expensive materials. Things like Incalloy 800 HT, which is about $42,000 a ton. Also, these fossil fuel costs are increasing over time. I don't know any energy company that is looking at their fossil fuel reserves right now and feeling very excited about it. So, you know, that cost of operating these older systems is going to increase as time goes on. Compare that against our photocatalytic light-powered reactor. At the reactor wall, where the LEDs are, it is actually room temperature and atmospheric pressure. And this is a function of us using a photocatalyst because we energize it with light instead of heat. And this means that we can dramatically decrease the pressure and temperature required inside the reactor. This allows us to build our reactors out of very low cost materials. The primary construction elements we're using in our reactor are aluminum and glass and plastic. So we can get up to a 20x reduction in raw materials cost. Not only that, using renewable electricity as the power source, the cost of renewable electricity is decreasing steadily year after year. So this is a trend that we're very happy to ride to success. And finally, what you see down here, you see, this notes on catalyst activity. Catalyst activity is a metric of how much product you can make per unit of catalyst. And one of the things that we have seen, and this is quite unique to Syzygy's plasmonic photocatalyst, is incredibly high catalyst activities, 15 to 30 times higher than traditional thermal catalysts. And what this means is that a very tiny amount of our catalyst can do a whole lot of work. So what Syzygy is doing with our photocatalyst reactors is we are making small, compact reactors built from ultra low cost materials that can run using renewable electricity and eliminate emissions. And you get a slurry of other benefits, on the operational side, such as you can start or stop the reactor quickly just by turning the lights on or off. So fundamentally, this is what we're doing. And this is all enabled by our breakthrough innovation, which is high performance photocatalysis. So our technology, plasmonic photocatalysis, specifically the antenna reactor photocatalyst, it was developed at Rice University by professors Peter Nordlander and Naomi Hollis. It's been published in Nature multiple times and also published in the journal Science. We've successfully completed grants from the U.S. Department of Energy's RPE program, the National Science Foundation. And what is perhaps the most exciting is that this is broadly applicable for many high-value, high-impact chemical reactions. And finally, from a timing standpoint, both photocatalysts and LED technology are kind of experiencing this step change in efficiency right now. So it's not just our photocatalyst, also LED technology is hitting a point that makes this possible today as well. So before we go forward, I'd like to take another step back and look at photocatalysis in general and talk about what brought us to this point today. So early on in the early 1900s, you start to see the first mentions of photocatalysis based around zinc oxide. And what you see is that this is really based around the textile industry. And so, we're more than a century ago, and what is happening is people are making clothes and making dyes, and they notice that these clothes and these dyes get bleached when they put them out in the sun. And so a number of scientists wanted to start investigating, what is happening here. But really in the beginning, nobody saw many practical applications for it. They started to understand photon flux, and they started to understand the chemical reactions that were happening, but they didn't know if they were able to do anything interesting with it. This changes, in the 60s, for many decades. What you see is that starting in 1972, Dr. Fujishima and Dr. Honda out of Japan, they observe water splitting with titanium dioxide. And you enter a new phase of photocatalysis based around actually doing chemical reactions, potentially industrially relevant chemical reactions using a photocatalyst. And really for many years, titanium dioxide dominates the conversation. And this is a semiconductor type photocatalyst, and it is the primary point of research for more than 4 decades. So unfortunately for titanium dioxide, it is neither a great light absorber or a great catalyst. It is only okay at both. When you look at titanium dioxide against something like the solar spectrum, it's really only good in the UV range, but for visible light, it struggles with absorbing. From a catalysis standpoint, it can do water splitting, but it can struggle with many other types of reactions. And because it is a semiconductor type photocatalyst, it has to overcome a band gap, which limits its potential efficiency. Then in the mid 2010s, there's another breakthrough. And what you start to see is plasmonic type photocatalysts. And many of these are able to dramatically outperform other types of photocatalysts. Our first work with Syzygy was published in 2016. And as mentioned, since then, we've scaled up the technology more than 500,000 times. And to kind of look at another way is, talking about the efficiency. If you go back into the 70s, most photocatalyst papers, people are struggling to get 1 or 2% energy efficiency. This is light to product. You start to see some improvements around 2010. You see things like the Department of Energy's Joint Centers for Artificial Photosynthesis, which is a $250 million Department of Energy program here in the US based around photocatalysis. But even in the early 2010s, you see people struggling to get above 10% energy efficiency. There was one notable paper in 2016, Nature Communications, where someone achieved a thermal or solar to hydrogen efficiency of around 30%, but the catalyst stability was pretty low, where the catalyst slowly decayed over time. And, there were some other issues with that catalyst. But then what you see with Syzygy's technology is over the past few years, we have managed to achieve energy efficiencies of 50%, and we have a very strong path to get this to 70%. This is huge because at around 70% is when we start to see true commercial viability for photocatalysis. We also have managed to overcome a number of the issues with scalability, stability, et cetera, that have plagued previous types of photocatalysis. And once again, we are a platform. We are going to talk about hydrogen, but we can do many, many things beyond just hydrogen. We aren't the only ones. So there are a number of other startups that are close on our heels. And if you're interested in the field of photocatalysis, I strongly recommend you go take a look at these companies as well. They're all doing fantastic work. Solistra out of Canada, NanoGap, I believe, is out of Spain, and Dimensional Energy is out of New York. And so we are a small but motley crew that is working on this, but we are making lots of dramatic improvements. So expect to see more out of all of us in the coming years. So to get back onto Syzygy and look at our development, I'm going to switch over to a video very quickly that will explain our reactor. And this will do a good job of letting everyone know how we work. Give me 1 second. Fantastic. So, as I mentioned, we have a plasmonic type photocatalyst. It is composed of 2 parts. The first one is our plasmonic nanoparticle. This is the larger light harvesting nanoparticle that you're looking at. It is decorated by smaller catalyst nanoparticles on the outside. So that is the light harvester, the plasmonic nanoparticle that just lit up. Those are the traditional catalysts that are used in industry. We use our LEDs to generate photons. That light harvester will catch the photon and transfer the energy to the catalyst. And altogether, that causes the catalyst to generate high energy electrons that are able to make or break chemical bonds. This fundamental process, we replicate a few trillion times a minute in our reactor. And this is how our technology works. As you can see, aluminum shell with LEDs on the inside. And then we have glass tubes that are filled with the catalyst that we energize. And at a high level, that is how the technology works. Go back to the presentation. Fantastic. So on the right side here, you can see our scale up over time, starting with milligrams in 2018. We made about 9 milligrams in our first tests, up to 5 kilograms recently. This is a more than 500,000x scale up. And you see that our energy efficiency is steadily improving. The new designs that we are going to improve energy efficiency with even further, we have not yet tested in 2021, but expect more improvements coming in the future. As far as the reactions we can do steam reforming, which makes blue hydrogen. We can do ammonia splitting, which makes green hydrogen. Dry reforming, we actually just won a grant for this, where we'll be taking CO2 to methanol. We have preliminary data on ammonia synthesis, and we can do a slurry of other reactions. So while we're most interested in hydrogen, we can do many, many other things. One question we always get that I would just like to address up front is why don't we use sunlight? I will say that ultimately, this is what we want to do. There are no technical limitations that prevent Syzygy from using sunlight. Our catalyst is very, very good broad spectrum, and we can get a majority of the solar spectrum from an absorbance standpoint. However, the problem with sunlight actually doesn't have anything to do with the tech. It has everything to do with the business model. Given intermittent production in an industry that generally likes to operate 24/7, you have to build absolutely massive facilities, which requires massive storage, which is quite costly. You at a minimum, you need a salt dome or an entire container field to store the product that you make. And all of this means a very high capital cost. And finally, in that capital cost, sunlight's very low energy, so you just need a tremendous amount of solar arrays. If you want to make enough, hydrogen for like a refinery, you start getting into conversations on square kilometers of solar collectors, and the cost is very high. I do see Syzygy getting into using sunlight to drive our reactions, but it will probably be after 2030. It is not good for a first product though, just because of the costs.
Trevor,
Markets we're going after.
A little time warning. You have about 3 minutes left.
Yeah, and don't worry, I'm good for it.
Okay.
So multiple markets we're going after. All of these markets are huge. Obviously, hydrogen is the first one we're interested in. The first products we will make will be for a distributed hydrogen system. So this will be small scale on-site hydrogen production. Imagine this at like a fueling station. We see two variations of this. One is where we are splitting ammonia to make hydrogen. The other is where we are using methane as a base, where we're using two different reactions together. We're calling this double reforming. We reform the methane to create hydrogen, then we reform the CO2 to create methanol. Ultimately, we see this technology because of the reductions in capital costs, the reductions in the cost of electricity, and the lower electricity requirements versus electrolysis. We see ourselves being able to achieve costs as low as $1 per kilogram before 2030. We also see ourselves being able to achieve better life cycle greenhouse gas emissions versus real world applications versus electrolysis, SMR, and others. We're very focused on carbon intensity. So if we have time during this call, I would love to dig into carbon intensity and how we calculate carbon intensity. We also take into account things like the carbon intensity of manufacturing the solar panels, the carbon intensity of installing the wind farms. And when we do this, we see that we are able to reduce carbon intensity on a life cycle basis. And then obviously we have comparisons. When we achieve our 70% efficiency, we will be very competitive on both cost and carbon intensity versus the alternatives. From a timeline perspective, we are gearing up for our demonstration system test later this year, towards the end of this year, field trials at customer sites. Next year, we'll be making a hydrogen station that can fill about 40 vehicles a day. And finally, followed by true product launch into the market in 2023 and beyond. We're getting lots of interest. We've raised $35 million to date. We have multiple grants and multiple customers interested in deploying our product. We have a fantastic seasoned team. I'd love to tell you about them if anybody has any questions. And I will turn the floor over to the other presenters.
Many, many thanks, Trevor. Very interesting. So, and meanwhile, some questions have already started popping up in the Q&A box, so we will address them later. But meanwhile, I'm now giving the floor to Ronnie for his presentation.
Thank you, Ilaria. I will try to share my very interesting presentation, and I even tried to get my slides changed at some point to what you said, so that's good. And you are sharing your screen. You see my screen?
Yes, we can see it.
Okay. So very interesting presentation, and I would say, and when Ilaria asked me and James asked me to contribute to this discussion, I was confused. Okay, what can I do for Photocatalyst? I had to dig into my courses on basic chemistry and electronics to find out what it's all about, and then I saw it, and I think I understand it to some extent. It might seem magic, but it seems to be physics to me, so that's a good point. And then I try to put it in the whole perspective of the race to the holy grail of hydrogen, of carbon neutral hydrogen. It's more today. It seems to be a holy grail. If we can find this, then all problems are solved. And if I learned one thing in my almost 40 years career now as a professional engineer, there is no silver bullet. So, and that's why I wanted to share with you some thoughts on what is it all about, where could this fit into the whole puzzle, and what questions do we need to solve to see where it can be put in and where it can solve problems, or where we have to raise more questions to find out what problems can be solved, and where it can bring extra value to the whole chain. So there is a need for hydrogen. Okay, there is already use now in industry, and in future some people think it can do everything, but it's not always the most appropriate route. And if you look at transport, it was already addressed here. Road and train, to if you look at the real view or what is happening in the whole system, there is very limited potential there. The electric vehicle is taking over. The electric trucks are there, but in navigation and aviation, there is a direct and indirect need for hydrogen via synthetic fuels. Trevor already hinted to it by methanol as one of the products that it could be made by this type of approach. Buildings, there's not much need for hydrogen, but in industry,
Ronnie, we are still seeing only your first slide, so the intro slide.
Shoot, what's happening?
Perhaps you could try to click again on slide view. Voila, perfect. Yes.
Okay,
it's working.
That's better.
I think it's not in slide view mode. Try again, please.
No, it's not in slide. Try to make slide view mode again. Is this better?
No, we can still see your entire presentation.
Okay, I will put it in slide not in slide view then, not to try find out why. Okay, is that okay for you to see? Can you read everything this way?
Yes, now we can see your slide 1. So I think you were already on slide 2.
So
yes, correct.
Okay. So as I said, the explanation, there is a lot of need in industry and a lot of need for synthetic fuels, for hydrogen as an intermediate product to get to, which was also said by Trevor, ammonia, methane, methanol, and that kind of things. Present use in Europe already 10 megaton hydrogen per year in different elements. I want to point that refining is one of the bigger users that may, of course, vanish in the years when we go away from fossil fuels more and more to electrifying things. Hydrogen production. How do we produce hydrogen today? Sometimes it's just a waste product. For instance, if you have electrolysis to produce chlorine, then you get hydrogen as a waste product. Coal gasification, black in Australia. Steam methane reforming, most of it today. Steam methane reforming, potentially with carbon capture and storage, which is then called blue hydrogen, which is also used as a term by Trevor, as they produce also hydrogen and CO2, which is blue. Then you have pyrolysis, what is generally called as turquoise hydrogen. And I think, Trevor, you should try to find the color for your hydrogen because it has no color yet. So there's not much left. So have a good thought. Maybe we could set up a workshop on that. And then you can go to green hydrogen from electrolysis if you are fully 100% green power, which will not be for the first decades to come. And of course, a lot of people expect an awful lot from biomethane as a source for negative, even if it's CCS, even negative emissions. Another point we have to look at is the TRL. It was not directly approached by Trevor, But where are we in the different routes that you described? I think, if I understood it well, there are so many routes and so many potentials that the TRL level of each of the products same level. But I would like to see that addressed, or we could have that in a discussion. What is available? Where are we for producing hydrogen, for producing methanol, for producing ammonia, for all the things that you are looking at? And then we have to make a comparison. And this is, for me, the most important question. If everything goes okay, we are looking for a how should I say, a route which is going to be in the atmosphere. And we all know that coal and steam methane reforming is massive amount or a lots of CO2. We all know that we can capture a bit. We all know that pyrolysis gives us carbon black. But also photocatalysis, it may give, I don't think, if I learned it now correctly, it doesn't give carbon black, but where are we? And electrolysis needs green electricity and needs water. For the pyrolysis, photocatalysts, and SMR, we need methane, we need natural gas. And we all know that methane and methane losses are a very big problem in the whole greenhouse gas balance. One unit of methane gives the equivalent of 25 units of CO2. So if your primary product is methane, you have to be very careful where you source the CH4 molecules from, because if there's a lot of losses along the route, even a CO2-free production gives you a very important greenhouse gas impact. So when again looking at it, where does it fit? It fits amongst all of these. So it's yet another kit on the block. It's not going to be the silver bullet. It's going to be one of the bullets, and I don't know how thick the layer of silver is on it. And you are all far too young, except for Jean-Michel, who have seen John Wayne. He had a silver bullet, and he could kill three natives, we have to say, not Indians, with one bullet. But I think we can't do that anymore. So we have to be very careful not to say that this is the solution, but it is a solution to part of the problem. From my point of view, if I look as an energy user, we look at the electrolysis is going to push very efficient applications of green power out of the system. This is not good. So electrolysis, I won't bet on it for the first 2 decades to contribute really to CO2 reductions. Photocatalysts and pyrolysis, we have to clearly, and one of my questions is, you was talking about efficiency, and you gently indicated that the efficiency was the amount of light per amount of product. But how efficient is your LED? How efficient is the overall megawatt hour of green electricity per CO2 unit avoided by producing hydrogen? This should be the measure that we all have for all the applications that we have. And it's not going to be quite easy. And economics, what is the cost per megawatt hour green electricity, per megawatt hour hydrogen produced? And a very interesting thing that you said, in between brackets, very fast, is that you can make the thing small. And I would like to see, there are a lot of small chemical factories in this world. I would like to see how you can plug in such a unit for delivering locally hydrogen. I'm not talking about transport. I'm talking about feedstock for small chemical companies, for food industry, where you need hydrogen. And then electrically wise, how dynamic is it? You hinted to it that it's quite dynamic, because in a sun and wind fed power system, if you can use very dynamically electricity, it's going to be filthy cheap to do so. So these were my 5 cents. There is no silver bullet. And to my feeling, this is not going to be the one because I've never seen one. But we have to evaluate it with different criteria: CO2 per product made, how does it fit in the methane strategy, what is the green electricity meet per product produced, and what are the economics, parallel streams. I've put carbon black here for pyrolysis, but also for methanol, as you indicated, or ammonia in parallel products. And what is the TRL level? When will we see what in which stadium? When will I see the first petroleum refinery, which is going to be close to 10 years, equipped with this one? Trevor, very intriguing, very stimulating thoughts, but in the overall system, where does it fit?
Thank you very much, Ronnie. That's I think much more than 5 cents. So thank you very much for framing the discussion. And I think, Trevor, you have the chance now to reply to some or all of the good questions that Ronnie raised. So please, you have the floor.
Yeah, so first off, thank you very much, Ronnie. That was a fantastic presentation, and I think that you absolutely hit the nail on the head. And something that I have been saying a lot recently is that this is going to take all of us. We all have to work together. There should not be infighting in clean tech. And is one of the reasons why I called out the other photocatalysis companies and said that you should watch them, because and even beyond just photocatalysis, like electrolysis and SMR with carbon capture, and all the different ways to make hydrogen and make renewable energy. It's going to take everything working together. Energy is very regional, and I don't think a single solution is going to work in all use cases everywhere. So where is photocatalysis going to work? I think that the answer to that is it's going to be a progression over time. You mentioned the interest in our ability to go small and our ability to use intermittent power. We also see this as some of our strong suits. And because of this, we think that the early adopters of our technology are going to be distributed users of hydrogen, users that are currently getting hydrogen trucked to them as a gas or a liquid. That is where we're going to start. And the reason is twofold. One is the elimination of the supply chain helps to eliminate cost. So we'll be able to give them a much, much lower cost of hydrogen, which is ultimately for the vast majority of consumers, the most important thing. Then versus other distributed alternatives like electrolysis, we will dramatically reduce the electricity requirements. For example, if you want to use an electrolyzer, it's about 50 kilowatt hours per kilogram. That's 50. For our systems, when we're using methane, it is about 15. And when we're using ammonia and doing ammonia splitting, it's about 10. So we get a dramatic reduction in the amount of electricity needed. This has a lot of interesting effects. So you need less grid infrastructure. That the grid infrastructure needed to make large quantities of hydrogen is not trivial. So reducing that is a huge benefit. And you also get less of our system needed. A smaller footprint can make just as much hydrogen. As time goes on, we do see ourselves starting to go into large scale. Some of the interesting aspects of our technology, like the ability to start or stop quickly, the ability to operate efficiently at small scale, that doesn't translate as well to like refinery type applications. As we've been talking to refiners, those systems are already in place. They run in a certain way. So for example, you can't start or stop a refinery quickly. It takes 1 or 2 days, and even though our reactor can do it, none of the components around it can. So in there, it will be a capital cost play, and an operating cost play. So reducing the cost of the equipment, reducing the maintenance cost, and also reducing emissions. So we do see plays for large scale infrastructure. And then finally, as I mentioned, running on sunlight. We are very interested in that. And as the market develops, we do see the ability to do that. However, we don't think that we're going to do it alone. As I mentioned, you need absolutely massive storage, like a salt dome or something. We see that we will probably be working with other hydrogen production solutions and maybe have multiple tied in with the same storage system. Because whenever you start talking about a salt dome, you're talking about storing, tens of thousands of tons of hydrogen at a time. This is like seasonal storage, storing hydrogen seasonally for like refineries and other large chemical applications. And as I mentioned, the capital cost is prohibitive. So it's not something that we would want to do on our own. But we see that happening probably, 2030s, maybe mid to late 2030s. So I also, Ronnie, I'd love to give you a chance to respond to that or ask any other questions. And we also have some questions from chat.
I'm not going to have this discussion. Two of us, other participants also, but I'm coming back to the efficiency. If you go from, and you already answered it for a certain part. So if you go from, it depends on whether you use methane at the beginning. If you could use ammonia, which is of course very interesting, but not easy to transport. There's not in front of us of an SME. There's generally not an ammonia pipeline around. But what's intriguing me and really is how much electricity do you need to produce the whole thing? Because what is the efficiency of the LEDs? Are just regular LEDs, or is there is something intriguing to me, that efficiency?
Yeah, so I'll tell you how we calculate efficiency, then I'll talk about LED efficiency, and then I'll talk about round trip efficiency.
Okay.
So how Syzygy calculates efficiency is we take in the overall energy and electricity going into the system. So all the joules and electricity going into the system, then any energy contained within the feedstock. So if we're using natural gas, or if we're using ammonia, it has a heating value. So both of those combined together against the total energy in the product. And in this case, that would be hydrogen. So we aren't playing any games in there. It's, the electricity at the plug plus the feedstock at the, coming out of the pipe against the final hydrogen produced.
Okay.
So that is how we calculate our energy efficiency. Now the LEDs, it's actually quite interesting. So a lot of LEDs use what is called a phosphor, and they turn the light from monochromatic to white. So if you have like LED bulbs in your house, it has this phosphor, which has an impact on efficiency. A lot of the white LEDs max out around 50% efficiency. That means 50% of the electricity that you're sending in is getting turned into photons. And LEDs set around this range for quite some time. We could talk about other lighting sources like, incandescent mercury lamps, but all of their efficiencies are very, very low compared to LEDs. LED is king on efficiency. Because of the marijuana industry, they needed to grow plants indoors, and they wanted to reduce the cost of growing plants indoors. The marijuana industry pushed the LED industry to start making more and more efficient diodes. Plants also, they can't see, they don't care about white light. It's all about energy transfer. And so the LED industry started doing monochromatic LEDs. So they eliminated the phosphor that I mentioned earlier. And starting around 2016, you started to see LEDs that could achieve 80% electricity to photon and beyond. Whenever we started the company, the very first days, we had one LED. There was a single diode on Earth that we could find that was in that efficiency range. Today, we've got 4. So we've got 4 different diodes we can use, and all 3 that have come out are more efficient than that first one. So we're starting to see more and more efficient LEDs. This is very much a material science problem, and there are also some implications on wavelength. So not all wavelengths are created equal. For example, green. For as much as we would love a green LED, the material needed to make green LEDs cannot achieve very high efficiency. And so like monochromatic green maxes out at like 20% electron to photon, which is horrible. We never use it. And so the wavelengths that we do use can achieve very high efficiencies. And then we tune our photocatalyst to work with that. And then finally, I mentioned round trip efficiency. So this changes depending on a number of implications. As Ronnie mentioned, the pipeline, like ideally anywhere there's a pipeline that helps with that a whole lot. So generally natural gas has a pretty good round trip efficiency. There's natural gas pipelines going everywhere. We can use it. You do have to do something with the carbon. Our play is that we're going to turn it to some kind of liquid like methanol or something else. On the ammonia side, we really only see ammonia being interesting when you're doing international import and export of energy. At small scale, like putting it in a tanker truck and driving it around is a huge pain in the butt, to say the least. There is no country on earth that lets you just drive tank loads of ammonia around for good reason. But when you look at the international import-export market, there is a very well-established ammonia supply chain, huge tankers, that go from, North America to Europe and in Asia to Australia and back and forth. We see ammonia being an energy carrier for energy poor areas. Good examples are like Japan and Korea. They import their energy. This would all be behind the fence, so consumers would never interact with it. You receive a huge tanker of ammonia and you decompose it there. Round trip efficiencies, we actually see this as being one of the most efficient ways to transport hydrogen. Liquefaction, you lose a lot of energy when you liquefy. There is boil off, and so you have to spend energy to keep it as a liquid, or you lose some of your hydrogen. And there's other transport considerations, like what you have to do when you get to the port with your hydrogen that is gasifying, how you get it into storage areas, how quickly you have to use it. And ammonia solves a lot of those problems. So overall round trip efficiency, we see ammonia being ideal for international import and export. We see the natural gas grid being ideal for areas that have access to low cost natural gas. The one thing that society is still not sure on is when you do use methane, what do you do with that carbon atom? And I say like, hey, we're going to turn it into methanol. It's interesting, but I don't have many use cases that I can point to where people are, taking a CO2 stream and turning it into methanol. And not only that, if you've got like a distributed market and you're making methanol in a distributed fashion, how do you handle that? It's not something that's been done before. I hope that answered the question a little bit.
Greatly. I would say there is more use case for ethanol, but that's called drinking. So, I think I would use a bit more energy also. Any other questions, Ilaria, from the?
Yes, I actually wanted to. First, a little curiosity also coming out of your own presentation, Ronnie, because at some point you mentioned methane emissions as one of the, let's say, the backsides of several technologies actually. So maybe I wanted to ask Trevor to elaborate a little bit on this, because this is also very important in the attempt to place photocatalysis somewhere in the taxonomy of that we are using to classify hydrogen and other low carbon gases. So where do we stand with methane emissions in photocatalysis? Can you quantify? Are there how many?
Well, so it depends on the methane source, and it depends on a number of different factors. And so I think that this would be a good time to take a step back and look at how Syzygy looks at overall carbon intensity. And when we think about carbon intensity, we think about 4 buckets. This is slightly beyond scope 1, 2, and 3, if you're familiar with that. But the 4 buckets we think about are all of our inputs. So this is the carbon intensity of the electricity, the carbon intensity of the methane, everything that is going into the system. Bucket number 2 is the carbon intensity of our system itself. So is the system producing any emissions? Bucket number 3 is the transportation. So getting the products that we make to end market. And finally, bucket number 4 is the end use. So we're making hydrogen, it's great, end use is carbon free, but if we do make something like methanol, what's it being used for? There's a difference if it's used for combustion or if it's used as a chemical feedstock. So around methane emissions, that would be in that first bucket I described. So different sources have different impacts. You can get anthropogenic methane from like a dairy farm or a landfill. Many regulatory regimes consider those to be carbon negative because otherwise it just goes into the atmosphere. If you're using fossil, you have to take into account, the production processes. You have to take into account the distance traveled. There is a lot of standard accepted leak rates for methane pipelines. And so there's a huge difference if we're importing it from Russia versus if we're getting it from the North Sea. All of that has to be taken into account. Not only that, I think over time we need to get into recurring certification where we're sending out drones to monitor the pipeline. We're actively looking for and controlling leaks and using a blockchain or some other distributed ledger to tie that certification that pipeline X feeding this plant has been checked and its leak rate is this, and use that to calculate the overall carbon intensity. And the reason why I didn't give you just like a flat out number is because it varies dramatically. If managed well, the leak rate can be very low and you can achieve very low emissions using methane. If not managed well, it can be absolutely abysmal. It is totally possible to exceed your entire budget before the methane even gets to your plant. It is also totally possible that if you have very low leak rates and you manage it well, you can achieve a lower carbon intensity than electrolysis using solar panels, for example. Nobody likes to hear those things, but it's true, and it's variable. Every project has to be looked at individually. Trying to say that this single use case fits the whole globe is not correct.
Okay, great. Thank you very much for this. So just speaking from the chat box, I saw that you, Trevor, already replied by typing to some of the questions. So that's very good. Well, there's a quick question, very peculiar. Is there a market for using this technology for space and or lunar applications?
We actually think like there's a huge application for space because you can get lots of sunlight. Okay. And given that the reactor can start or stop quickly, things like that, whenever you're in the bright side of the earth, you could do chemical reactions. We see applications for life support. Like if you think about life support, you've got CO2, you've got, humans give off all kinds of interesting things. You've got like ammonia you have to deal with. You've got all these interesting reactions that keep people alive in space. And we've shown some capability on that. So we're quite excited about space. However, that's like a long shot thing. I'm not even going to give a timeline for when we're going to work on that.
Okay, I can
understand. But it does inspire the imagination.
Good. So many applications, and you have also other questions regarding applicability. I leave them to you, maybe separately. There is one interesting comment that is actually something I wanted to ask you as well from Laurent. Photocatalysis is also able to split water. Research efforts are in fact mostly dedicated to this reaction. To be honest, when I started researching on this, I found more this as a, say, work stream for photocatalysis, water splitting, which would be wonderful because then you wouldn't have even the fossil fuels to be used in this process, and then you would really get different numbers and different outcome of the reaction. Any comments, any reflection?
Yeah, so we have been interested in water splitting. We have decided not to pursue it, and it has nothing to do with the photocatalysis side. For us, or for our photocatalyst, we like to do things in gas phase, and just this is because we can achieve very high activities whenever we're in gas phase. We don't really know how to get the oxygen and hydrogen apart after the reaction happens. And to do this, you generally need, you need to be in a liquid solution. You need to be in a cathode and an anode. All of the water splitting tech that we've seen has very low activities. Going back to capital cost, you'd have to cover many square kilometers with these collectors, and we were never able to make the economics work. So we have put that one on the back burner for now. Going back to the dream, you go to 2050. The dream is absolutely using photocatalysis to do like large scale water splitting, but the technical challenges around getting the hydrogen and oxygen apart after the reaction happens are not trivial. And whenever you do something in a liquid bath with the cathode and the anode, those setups, all the ones that we have seen are very high capex, very low activity, and it makes it challenging.
Okay, great. So we are a little bit behind there still. Good, Trevor. I think we are very close to the end of our online debate. So I will give the floor to Ronnie for any Ronnie and Jean-Michel for any final consideration. And from my side, I just wanted to say a big thank you for this very, very interesting insights. Let's be in touch and tell us how this technology progresses. A big thank you also to Ronnie Belmans for bringing us back to earth with technology and economic consideration. Thank you very much. So that's all from my side. Just a final thanks to James Kneebone as well, who helped on the scientific organization of this event. Thank you very much. And I give the floor to Ronnie first and then Jean-Michel for conclusions.
Trevor, very interesting discussion. I learned an awful lot. And it's going to be one of the things to look at it very carefully, to take it on. And you set up a timeline. Let's have some tryouts in distributed way by 2030, see what happens and see where we need it. So it's it's interesting. The one thing which was also on the chat is how does it compare to pyrolysis? And I would like to have a chat with you on that offline. Where is what?
Yeah, so quick answer for that for everyone on. So from an electricity consumption standpoint, it's similar electricity consumption. From a capital cost standpoint, we will have dramatically reduced capital cost versus pyrolysis. Carbon intensity, it depends on whether or not we utilize our CO2 and turn it into methanol. If we don't, then we will have a higher carbon intensity than pyrolysis. If we do, then it will be similar. So, and Ronnie, I would love to jump on a call with you afterwards.
Okay.
And dig into that, because the nuances behind what I just, I'm just totally like glazing over a 2-hour conversation in 10 seconds.
We'll set it up.
Fantastic.
Thank you, Jean-Michel.
Yeah.
Final remarks.
Just an anecdote. I will be 72 this month, and I am a researcher. I love research, and I'm attending many meetings, many things. And now the conclusion. I will give you the gold medal of FSR talks we started last year in September, because what you did is exactly what we are dreaming. There is an issue, there is an innovation, there is many possible angles to make it a business and to contribute to this or that policy. And we need an excellent debater like Ronnie, being a good researcher, but also an innovative company, that's the company of Trevor. And it's only in this dialogue that we understand where we are going to. And it's a wonderful outcome. And I'm extremely happy for this. And of course, my gold medal will be immaterial. It will be a bit digital. But nevertheless, I would like to applaud you in public because it has been wonderful. And good luck to your company, Trevor.
Hey, thank you. Thank you so much. Thank you for having me. This was, a lot of fun. If anyone on the call is interested or would like to connect, please feel free to reach out to me on LinkedIn. And looking forward to engaging with you all in the future. And hopefully we get a project up in Europe before too long. So see you at a hydrogen station soon.
Thank you very much.